Hi, my name is Jessica Donahue, and I worked with Dr. Ben Lee and Dr. Stephen Hayner on finding the maximum surface area polyhedron with 5 vertices inscribed in the sphere. We determined that the surface area of the convex hull of the points is maximized by a triangular bipyramid with 2 of the 5 vertices placed at the north and south poles, and the other 3 forming an equilateral triangle inscribed in the equator. This result confirms Akiraju's conjecture. We proved our theorem, which states that the surface area of such a polytope must be less than or equal to 3 square roots of 15 over 2, or approximately 5.81, with vertices at positive and negative E3, meaning the north and the south poles, and the other 3 forming an equilateral triangle with its vertices at E1, zeta 1, which is defined by negative 1/2 the square root of 3 over 2 and 0, and zeta 2, which is defined by negative 1/2 negative square roots of 3 over 2 and 0. This image on the right shows the maximum surface area polytope with 5 vertices, which is formed by taking the convex hull of the north and south pole, which is the positive and negative E3, and an equilateral triangle in the equator with vertices E1, zeta 1, and zeta 2, as shown right here. This chart shows the other cases of V vertices that have or have not been proven. As we can see, cases V equals 4 with the regular tetrahedron, V equals 6 with the regular octahedron, and V equals 12 with the icosahedron were able to be proven optimal. They were proven optimal using an inequality that portrays the maximizer when equality is reached. However, no such polytope reaches equality in our case of V equals 5. Thus, we had to use a different approach in order to determine the answer. We began by determining the necessary geometric condition that the maximizer must satisfy, which says that the projection of the apex or apexes onto the plane containing the other vertices must be equidistant to all of the edges in that plane. We also used the fact that in the case of 5 vertices, there are only 2 combinatorial types of polytopes. The 5 pyramids, which are the polytopes with 4 coplanar vertices, like the standard image of a pyramid that we think of today, and the 5 bipyramid, like the image pictured in the previous slides. With these, we were able to optimize the maximizer for each of the combinatorial types using Lagrange multipliers method for optimizing a multivariable function. Then we compared the 2 optimal surface areas in order to determine the surface area maximizer for 5 vertices, which was the 5 bipyramid, with the surface area being approximately 5.81. Our project applies to a fundamental concept of crystallography, which refers to the configuration of Lagrange atoms in the sphere that are bonded to a central atom called the coordinate hedron. Using the concept, they are able to determine a formula to determine the volume discrepancy, which is shown here by this formula. The same concept can be applied when defining idealness using surface area, and thus resulting in the surface area discrepancy shown by this equation here. More specifically, we are able to develop an equation to determine the surface area discrepancy of any coordinate polyhedron by the formula shown here. You can view the preprint to our paper to see more information on how we proved that the angular bipyramid is the optimal 5-vertice polytope. Thank you. Bye.